So good morning, everyone. Uh, it's already 11, so we will start our session. This session is 1.5 hour long with 6 presentations. This session is about modeling-based decision support system. So my colleague Nitin Bashi and myself will be running the show, and we will try our best to finish on time, if not before. I really expect cooperation from all the presenters. We have 6 presenters, as I mentioned earlier. Without further ado, I have already requested them to be in the front. They are representing different agencies and institutions and countries, one from Ethiopia, one from India, and from Singapore, Japan, Germany, and Netherlands. We have really a multinational team with diverse set of expertise with us as a speaker and as a panelist. With this very brief background of the session, there are a couple of rules for the presenter. Like they are already invited in the front. You will have 10 minutes for the presentation, and we will help you to keep the time by letting you know about 2 minutes before the completion. If the time is over, we request you to move to conclusion so that we can finish on time. We can take 2 to 3 questions, short questions, immediately after the presentations. And if you have more questions, you can keep it, and we will have a panel discussion at the end where we can discuss more in detail. Also, I will request all the speakers to think of one key message, which I will ask you at the end. How your work you are presenting is related to the theme of the conference. Adaptation and resilient development. You don't need to tell now, you can just present your contents, and at the end, for the final message, we expect you to tell that in 1 or less than 1 minute. So you can think right from the beginning. With this brief information about the session, my colleague Nitin and myself would like to move ahead. The first presenter we have is, apology if I mispronounce your name, Dere J. Hailu Asfa. From Addis Ababa University, Ethiopia. He will be talking about optimal operation of hydropower reservoir. Please go ahead.
Thank you. My name is Dereja Hailu. As said, we did his work with Fikro Fantau. And the topic of my presentation, slightly modified, but it's almost the same: hydropower reservoir management under climate change. This is the structure of the presentation. So as you all know that hydropower is an important source of energy. It's clean and renewable. For hydropower generation, then we need, in most cases, storage structures or reservoirs. And this role of reservoirs is to match the supply and demand in space and in time. And their management is very important, in particular, the operation of reservoirs, in order to reduce vulnerability and also to make an efficient use of the water resources. So climate change affects this practice and the management as well as operation of reservoirs. As you know, precipitation and temperature are changing. This has an impact on the hydrology. There is a shift in seasonality of flow. So all this means the reservoir management, or in particular the operation, would be affected, would be impacted. Just to set the context, why we have undertaken this study in Ethiopia. As you see, surface water availability, and there is a huge potential owing to the surface water and also topography. Ethiopia has a big potential, huge potential. Currently 90% of the electricity in the country comes from hydropower. And you see the trend of development of hydropower in the country. So 10 years back, it was something like 2,000 megawatt. Now it's about 4,000, greater than 4,000. And in few years, in 2 years, it would be over 10,000 megawatt. And there is a huge hydropower development in the country, including the construction of the Great Ethiopia Renaissance Dam, GERD, which alone generates more than 6,500 megawatt. So understanding and evaluating, assessing the effect of climate change on the planning of reservoirs to be constructed and the management, in particular the operation of reservoirs existing, is very important for the country. So with this background, then the objective of our study is to assess how this climate change impacts the hydrology, which is a very essential input to reservoir management, reservoir operation, and also determine how best do we operate these reservoirs, or optimal reservoir operation. So we selected the Tekeze hydropower dam as a case study. This dam is designed with stationarity assumption, and also we have observations that this reservoir has not been operated optimally. So some words on the study area. It's part of the bigger Nile system. The Tekeze River is a tributary to Atbara and then eventually joins the Nile. It contributes about 30% of the flow. So water resource availability, 8.2, and because of, again, the topography, then there is a high potential in this particular river basin. 15 potential hydropower development sites have been identified. And among these, only one of them is developed, constructed in, I think, 2009. The one you see in the blue triangle is a dam, our case study, the hydropower dam. We call it TK05 with an installed capacity of 300 megawatt and max storage of 9.3 billion cubic meter. So it's the upper part of the Tekeze. So the methodology we used is first obtain this climate projection data from Cordex Africa for 2 different climate scenarios, plausible climate scenarios, and we did some bias corrections using different techniques. We also calibrated and validated a hydrological model, the SWOT model, and then this bias corrected projected climate data is used as an inflow to the reservoir, and using our reservoir simulation and optimization model, which is HEC RES PRM, prescriptive reservoir model, then we were able to determine how best should these reservoirs be operated. So some results, the bias correction you see, once you correct the biases, then we assess how the climatological variables are affected in the future. So precipitation, the above graph shows us precipitation. So 2 rainy seasons, for one of the rainy seasons, and we have a decrease. For the other, we have an increase. But generally, annually, we have an increase in precipitation in the Tekeze Basin. Of course, temperature is increasing. The calibration and the validation of the hydrological model, as you can see here, good performance. Then with the projected climatic variables, we run our model for the near future time until 2040, and see how the stream flow behaves, how the hydrology changes. So definitely climate change has an effect on the hydrology and the water resource availability of Tekeze Reservoir. So the one you see on the right are the graphs, the hydrographs before and after the construction of the dam in 2009. So that has also benefit to downstream country, to Sudan. As you can see that we have a regulated flow throughout the year, and the farmers, the irrigators in Sudan are benefiting of this because of this dam. Then the reservoir operation. So we have identified the baseline period to be immediately after the construction or the commissioning of the dam, which is 2009. to 2017, we have observed data. So you see here the observed and optimized storage levels or pool levels of the reservoir. So the blue is observed and the red one is optimized. So if we operate these reservoirs optimally, you can produce more power on the Takazia River. So then what we did next is for the projection or the projected time to the near future. Again, you see the green and the red curves are the optimized curves for the two different scenarios compared to the baseline. Still, we have more power stored. We have more power storage in the future, meaning we can produce more power compared to the baseline period. So one thing, inflow is increasing, and the other thing is also the way, if you optimize the way you operate the reservoirs, then you have maximum power production. So as a conclusion, we know that the two climatic variables are increasing. This will lead into the increase into the flow, but this only is not enough to have maximum power production, but we need to have an effective operating rules or adaptive operating rules, and with this we can produce more power in the future. So the message here is that the climate change will affect the future reservoir plannings as we are constructing and will be constructing more dams in the basin. It's very important to consider planning and as well as the operation of reservoirs in face of climate change. So climate change is a very important factor in planning and designing management of reservoirs, hydropower reservoirs in the future. Yeah, thank you.
Thank you so much. Let's give a big round of applause for finishing on time. Really appreciate it. Now we can take a couple of questions. We have 2 minutes left. If anyone has any query or maybe additional inputs in his presentation, we really appreciate it. Any questions? I request my colleagues to help with moving the mics. Yes, please. You can use this one.
Thank you. This is Zulfikar from Bangladesh. I'm the lower riparian country in the Ganges, Brahmaputra and Meghna basin. So earlier in this room, there was a session regarding whether hydropower is a game changer or not with the perspective of climate mitigation. And the panelists were not concluded in the concrete solution, but they...
can you please be specific to the question? We have very limited time.
So
Thank you.
My question is that whether you have modeled, the changes, potential changes of the operation rule. So did you include or consider the potential impact in the downstream areas to, analyze the sensitivity of the operational rule? That is my question.
Yeah.
Thank you.
So good question. Yeah. So in the model, we have put constraints so that downstream releases are ensured all the time, and also environmental flow requirements are met. Yeah. So with that, we're in the model we address these two elements. Yeah. Yeah.
Any other questions? If not, I have a quick question to you.
Yeah.
In many cases, reservoirs can help to alter the inflows due to climate change, right? So did you analyze something, or do you have some insights whether these reservoirs you are under your study are really helping to moderate the alteration due to climate change?
We didn't do that, but what we have done is taken the climate projected data and run our models, and then have the inflows, the projected inflows into the reservoir, and with that we're optimizing the operating rules. But what you are mentioning is a very interesting to do.
Thank you, sir. Any other questions? Quick one, the last one. If not, thank you so much. Let's give a big hand to him. Now, the next presentation is from Ravi Kumar Gupta. He will be talking about complex networks for modulars of the compound extremes. He is from Indian Institute of Technology, Roorkee in India. Yes, you have 10 minutes as well. Thank you.
Good morning. My name is Ravi Kumar Guntu. I'll be talking on the applications of complex networks to quantify the modulators of compound extremes. The outline or the overall crux of the presentation will be on the advantages and limitations of the methodology, and I'll be showing one application to Indian summer monsoon. Compound extremes. It's a new term which was coined by IPCC in 2012 report, where it is defined as the simultaneous occurrence of two or more hazards at the same place, while potentially causing a significant impact on the ecosystem. For example, SST variability in the Nino 3.4 region can modulate the location and magnitude of the drivers, say precipitation and temperature, over a given region, while causing a change in the magnitude and the frequency of the hazards, and it causes a significant impact on the agricultural productivity. A detailed background and review on compound dry and hot extremes is described in our paper, and in this particular study, we have questioned how the frequency of compound dry and hot extremes is changing during the recent decades. We observed there is a threefold rise in the occurrence of dry and hot events, particularly in the food belt of India, north central India. There are three reasons to this frequent occurrence. One is increase in aerosol content, and the second one is rapid warming of Indian Ocean, and the third one is the travel of depression systems is reducing. And in addition to the frequency, what we have observed is there is a huge widespread spatial extent of the occurrence. This has been conducted using an empirical approach. When a compound hazard occurs in India during the summer monsoon, the study by Mishra et al. Has shown that there is a significant reduction in the agricultural productivity, particularly in the food grains like rice and wheat, which contributes 90% of our consumption, food consumption. So with this background and motivation, I've tried to study what are the modulators that are creating the frequency in India. So for this study, I would say, however, there are many studies that are there previously which have quantified the modulators, particularly say Nino 3.4 region is very well known for the core monsoon region. However, for the non-core monsoon regions like northwestern India, it is still a question which region is influencing. So to this, we have developed a methodology, and the methodology consists of three variables. First is SST region, and then the second one is precipitation and temperature for a given region. And we have considered 1960 to 1990 as our base period recommended by WMO to track the climate change, and using that period, we have derived SPI and STI. The methodology goes in this way. For the 30 observations at monthly time scale, we fit a distribution in general gamma distribution, and then we convert that cumulative probability into standardized values. And the physical meaning of this SPI is, during that particular year, at that particular region, to how many standard deviations the anomaly is. And it's the same case with the temperature. The physical meaning is to how many standard deviations the anomaly is. And we define compound event as the simultaneous occurrence of SPI less than -1 and STI greater than 1. This is defined as a moderate compound dry and hot extreme. So the question is, why only -1, why not -1.3 or 2? There is evidence that it has shown that even a moderate compound dry hot event causes significant reduction in the agricultural productivity. So Further, we have considered the events, and we have looked at the SST phenomenon as well. Say, for example, consider this as an Inno 3.4 region, and then the bars represent that either it is an El Nino or a La Nina. We have analyzed individually. And then this is an equation which describes the coincidence between the events on land to events on sea. And then how it is different from the previous methods. In the previous methods, they have used simple correlation coefficient to understand how the sea is modulating the land. The first thing is the correlation coefficient looks at the overall variance explanation by sea to land, and then the second approach is the tail dependence analysis, which comes with this distribution of fitting, and then here our analysis is purely based on the events, and then we do robust significance analysis, and then we come up with quantifying the coincidence between land to sea. And we have published a paper recently in 2022, and then all the paper is on coincidence analysis between the two variables between soil moisture and precipitation. And now I'll go into the application of complex networks here. Once we define the coincidence rate between land to sea, we develop a matrix from every grid point on land to every grid point on sea. And then we have these values, which says that 0.6, the meaning of 0.6 is that 60% of the time, the sea is influencing the occurrence of dry hot events on land. And here, this is a subjective threshold, 0.6. Still, we are working on it, how to make it objective. And the one represents a connection, which has a value greater than or equal to 0.6. Connection from sea to land. And then, upon summation, we say that the number of grid points that are contributing to the occurrence on that particular land point. And we have considered Indian summer monsoon and homogeneous regions of India, which was developed by myself, published in Journal of Hydrology. So we are looking at the effect of SST on the Indian summer monsoon or homogeneous regions of India. So a quick result from this application, what we have found is there are local connections as well as there are long-range connections. And still we are working on it to quantify the reliability, and we are working on the robustness. But a preliminary result is we have identified during the summer monsoon season. Yes, and thank you. And this particular map will show you to which part it is connected to. And to conclude, what we have observed from our studies, there is a threefold rise, widespread rise in the frequency, and we have developed a new method by integrating event coincidence analysis with complex networks. And the potential applications from this approach, it offers a fresh perspective in unraveling the teleconnections of compound extremes. And it helps to develop new customized indicators for every other region as well. And we are looking at the main application of predicting it. So once we have an indicator, we can simply use a logistic regression model, and then we say, what is the probability of the occurrence given the phenomenon of SST? And then with the message of how it can useful for this decision making for climate adaptation is that once we come up with the probability of the occurrence, then the insurance people or the agencies can look forward how we can adapt to that situation. And with this, I thank and I gratefully acknowledge the financial support from PMRF, Minister of Education, Government of India, and the data provided by Indian Meteorological Department, and all the references are provided in this QR code. And I would be happy to receive constructive comments and suggestions, and I'm open to questions. Thank you.
Thank you so much. We really appreciate all the speakers being so precise on time, exactly on time. Thank you. Now the floor is open for question and answer. We can entertain 2-3 questions as long as time allows. Any questions? I cannot see this slide. Yes, please.
Thank you very much for your presentation. My comment is, or question is about the base time period of data. Normally now it's used between 1962 till 1990, but we have already something like 30 years of gap. And most of the scientists or also organizations suggesting that to take a base time period of data closer to the research period, as long as you have good data. Now, why you haven't used, for example, data from 1990 till 2020 as a base time? Thank you.
Thank you for this wonderful question. You know, I'm aware that the WMO has recommended the period 1991 to 2020 to reflect the better changing climate conditions. We are looking at that hypothesis as well, how the teleconnections are varying if we change the period. So the period which I have shown is just a set of experiment. We are also working on the recent 30-year decade, and then we are trying to understand, are the teleconnections static or dynamic, or how they are changing with time. So we are also working on it. Thank you.
Thank you. Any other questions? Can I ask one? Yes, please.
Well, thanks for the presentation, and I already see that you have progressed quite well and also published a work. Just, you know, for my interest, I mean, you say that the dry and hot extremes are compound, you know, kind of event. Why you say so?
Because when we look at the evidence published in good journals, which says that particularly during some years, the productivity of agriculture has significantly gone down. And then when we look at that event with other events where only dry event has happened, we haven't seen that agricultural decline. The productivity, there is no decline in the productivity. But during the years when it was compounded by hot extremes, we observed that the productivity has gone down. So that is where we have seen that this is a compounding effect coming from dry and hot conditions.
Thank you. I think in the interest of time, also I can't see any hand raised. We will conclude here. Before that, what is your definition of compound in your study?
So in my study, I define compound event as simultaneous occurrence of dry and hot events at the same region.
All right, thank you. Thank you so much. Let's give a big hand to him.
Thank you.
Now, third presentation we have is from Rachel Ko. She will be talking about co-simulating water and energy system. She is from Singapore University of Technology and Design. Yes, please go ahead.
Okay. Hi. Good morning, everyone. I'm Rachel, and I'm from the Singapore University of Technology and Design. So today I'll be presenting my work on advancing the integration of renewables by co-simulating water and energy systems done by myself and Dr. Stefano Galelli. So before I start, when we look at the title of the presentation, we can see that effectively what I'm contributing in this work would be a framework that co-simulates both the water and the energy systems, which I think people have been trying to do. But in our case, we explicitly model it together. So to begin, I'd like to introduce the reservoir operations. I'm sure all of you are very familiar with how reservoirs work. So this is a typical layout of a hydropower plant. So on the left, you see the reservoir whereby we have the water storage. So basically water flows through the penstock, turns the turbine, and generates electricity such that it powers the electrical system. And on the right, that is where we release the water. And there are a few working equations that I would like to introduce because it's important for the operations. Okay. So first of all, how do we determine how much water to release? So typically in Southeast Asia, we follow a rule curve. So we have target water levels for 365-day calendar years. So we'll try to release water such that the storage is as close to the target as possible. So these are the working equations. So this is the mass balance equation whereby the storage of the current day, day t, is a function of the storage of the previous day, t minus 1, plus the inflow to the reservoir, and minus the controlled release as well as spills and evaporation from the reservoir. So naturally, this is subjected to constraints such that it cannot be beyond the capacity. And on the right, we have the hydropower equation. So the amount of hydropower produced would be based on the turbine efficiency, water density, the amount of release as indicated by the rule curve, as well as the hydraulic head. So here, what we can see is the influence of water on power supply. So next up, we'll look into the operations of the power system. So a typical power system model uses mixed integer linear program, MILP. So the goal is to supply all demands at minimum cost while complying with the technical constraints of the transmission network. So there are two questions that need to be answered. First, which generators should be used? And second, how much should each generator generate? So for the first question, it's unit commitment, which means that variables that we have are integer. They're either 0 or 1. So the cost that we're looking at is either on a switch, which would affect the fixed cost, variable cost, as well as the startup and shutdown cost. As for economic dispatch, they are continuous. So we'll get the production, which is the fuel cost, as well as the imports. So that affects the import cost. So whatever that is highlighted in red over here would be the sum of the costs that we need to minimize. So now, we're looking at coupling of models. So in the state of the art, we actually already coupled models, but this is called a soft coupling, which means that there is a one-way flow of information from the water management model to the power system model. So the water management model actually creates a boundary condition whereby we know how much hydropower is available, and based on that, the power system model would then choose how much to dispatch to the system. And what we are proposing in our work is to have a feedback from power system model back to the water model. Why? So I'll give you two reasons. So first of all, the boundary conditions, which is the available hydropower, may not be fully dispatched. And the second reason would be that given the increase of renewables in the grid, so we have things like solar and wind. So solar and wind energy cannot be stored, which means that whenever it comes, it has to go straight into the grid. So what would happen would be that it will result in problems of electricity oversupply, and this would cause forced curtailment or grid congestion whenever the grid is not able to transmit all the available hydropower. Therefore, what we suggest is that perhaps we could use the hydropower reservoir as a buffer, whereby we can store water whenever it's not fully utilized, and we'll release it after that. So this is the framework that we are using. So on the left, top left, we have the water management model, which comprises the equations that I showed just now. So the output will be the available hydropower. So this piece of information, together with other inputs such as solar, wind, load, and thermal properties, would go into the power system model. And from there, the power system model would decide how much of oil, coal, hydropower, and other renewables would be dispatched to the system based on the demand. So typically, the water management model works on a daily basis, and for the power system, it's on hourly basis. Okay, so what we are proposing is to add in a reservoir reoperation model, which will look into this particular question, whereby we ask whether the hydropower is fully utilized. So if it is, then it is ideal. We will just release whatever that has been calculated prior. However, if it's not fully utilized, we propose a framework that recalculates. So we have an algorithm that recalculates the release such that we would only generate the amount of hydropower which is required for the particular day D. So then everything will be updated, the storage will be updated, the release will be updated, this goes back into the model, and then the operations would then move on to the next day. So we tested our grid on the Cambodian grid. So basically, we are looking at a country that is small enough for us to model the entire country, but we want to look at something relatively large scale, whereby it's at a nation scale. So Cambodia, this is a 2016 grid. It uses hydropower. It has 6 hydropower plants, if you can see the blue dots over there. Okay, yep. And it has coal, oil, imports from surrounding countries, including Laos, Vietnam, and Thailand. And since the country is looking to decarbonize its grid, we actually added in arbitrary nodes for solar. So we have 2 nodes over here, which means that we have the as-is grid and the grid with 300 megawatts of installed solar. And just for comparison, we have a third case whereby we have 600 megawatts of installed solar. And here comes the results. So it's actually stacked bar plots. So it has two axes, the primary axis as well as the secondary axis. So the bar plots, the height of the bar plots follow the primary axis, which is the generation mix over a year. So as you can see, they're all the same height, which means that all the demand is being fully fulfilled. Yep. So one thing to note is that, okay, so the blue bars indicate the amount of hydropower that is being dispatched within the system. So on the x-axis, you see that every two bars share the same infrastructure, and the second bar is the one with the feedback mechanism added. Okay, so as you can see, every second bar means that as long as you have a feedback mechanism, the system actually performs better in terms of incorporating more hydropower in the system, as well as if we look at the right axis, we have the operating cost as well as the carbon emissions. So operating cost goes down, carbon emissions go down. So one interesting takeaway will be between the first, second, and third bars. In the third bar, we actually added solar. So as you can see, the benefits from less cost and less carbon emissions can be better if we operate the system in a better manner as compared to adding another solar plant. So in this way, of course, this is a deterministic work. Yep. We can kind of conclude that adding a feedback to the system allows operational flexibility, gives us lower operating costs, lowers carbon dioxide emissions, and also, even though we're doing it at an operational scale, we can use it to test management and planning solutions as well. So with that, I end my presentation. Thank you.
Thank you so much. Let's give a big hand to her as well. Any questions or discussions based on this presentation? Come on, I can't see any questions in the last two presentations also. Or it's too clear or not clear at all. There could be two extremes, right? If anyone has any observation or suggestions or the questions, yes, please.
So thank you very much for the nice presentation. My question is, okay, what happens if there's a flood? Since you're not using the water just to incorporate the solar and all, there's more water in the reservoir. So what happens after that?
Okay, thanks for the question. So that is definitely one thing that we have looked into, but yeah, I've not put it up here. So one thing that we realized is definitely if you store more water, so this is deterministic, but we actually did it for probabilistic. So we ran it for 1,000 different simulations whereby we have different inflows and all those things. So we encountered cases whereby there were way more inflow. So what happens is that because we store more, we tend to spill more. So definitely that is what we don't want. But in our case, in this case, we are trying to form like, this is an upper bound of the performance of how well things can be. So naturally, in a practical sense, things will have to be tweeted a little bit more. Yeah, such that, you know, if it's rainy, we need to release, even though we are sure that, you know, it will be curtailed, let it be. Yes, to accommodate for different objectives. Yep, I hope I answered your question.
Thank you for your presentation. My question is, you run the two models, the water management and the power model at a different time scale. The water management is daily, and then the power model is hourly. So how is the feedback working? Are you aggregating the power model? And if you do so, how does the performance?
Okay. Okay, yeah, thanks for the question. Okay, I can't really move it, but if you look at the framework itself, so the power system model is run at hourly. Therefore, when we look at the amount of dispatch hydropower, we aggregate it over 24 hours. And then we return this piece of information back to the water model, and it will reoperate daily. Yep, so it goes both ways.
Thank you. For all questions, we can entertain during the discussion session later. Thank you.
Okay, thank you.
Now we have another presentation from Firas Aljanabi. Yeah. No, sorry, Raksmi An. Sorry. So the presentation is about the climatic variability and dealing with Tonle Sap Lake Basin in Cambodia. He's working with the Tokyo Institute of Technology in Japan. Thank you.
Okay, thank you for the introduction. So, yeah, good morning, everyone. My name is Rex Mayang. So I'm from the Tokyo Institute of Technology, but originally I'm from Cambodia, which is a neighboring country of Thailand. So today I'm going to present one of my research, a part of my research, which I'm doing PhD. So which is about decadal climate trend, variability, and hydrological influence in the Tonle Sap Lake Basin. So we try to see how the variation of the climate variable, for example, precipitation or temperature, could influence to the hydrological, for example, stream flow pattern in the river basin. So this content of today's presentation. So we will start with the background of the study and the motivation of the study and information of the study area and some tools and techniques we use to do those analyses. And of course, the result which is about the variation or trend of the temperature and precipitation and how it can influence on the hydrological pattern. It's not well. So yes, nowadays we are talking a lot about the climate change, and usually temperature is one of the climate component or climate variable that usually address to see the evidence of the climate change. For example, from this figure, you can see I took it from the IPCC report. This is the average surface temperature on the globe on annual time scale. We can see that on average around 1 degree Celsius of temperature has been increasing. So this is the truth. We cannot argue. So we can. This is the evidence of the climate change. Temperature has been increased. And another thing, for example, precipitation might also have been increased or decreased. It depends on the spatial scale. So when those change, when the change of temperature or precipitation, it might also impact to the water resource availability in the certain river basin. And you know, the consequence of those changes have significant impact on the country in the tropical region, for example, in Cambodia, because the economic development, agriculture is heavily depend on the monsoon rainfall. So if monsoon rainfall, it change the pattern, so it also impact to the agriculture production and of course the national economic development. For example, in recent study in the Tonle Sap Lake Basin, they have found that the inundation area of the floodplain have been decreasing because of the changing pattern of precipitation. Although those changes might attribute to multiple driving factors, for example, the influence from the Mekong mainstream flow into the Tonle Sap lakes or the anthropogenic activity inside the lakes. But information around the 11 tributary of the lake still limited. So that's why this study we try to see how the climate variation in terms of precipitation and temperature might impact to the flow into the lake. So yes, the study area was conducted in the Tonle Sap Lake Basin in Cambodia, which is the largest freshwater body in Southeast Asia, with the basin area around 80,000 square kilometers. And this basin plays an important role in economic development in Cambodia. And the uniqueness of this river basin is the seasonal river flow. So the flow in rainy season between May to October, so the flow from the Mekong mainstream will flow into the lake. But after the monsoon finishes, for example, in November, the flow will flow back into the mainstream and into the Mekong delta. And this unique river flow creates enabling environment for the ecosystem in the lake. And of course, it will provide the benefit for the people who living around the lake and economic development in the country. So this is some tool and technique that we use to do the analysis. So the trend analysis, we use Mann-Canal test. And the hydrological model we use to simulate the flow, which we call soil and water assessment tool or SWOT model. So this model have been validated and calibrated in this study for this study area from my another study. And there are two main or important data that we have been used in this study. One is precipitation from the IMERGE, which is satellite-based precipitation, and the temperature from the SAOBS, which is the gridded temperatures data for the Southeast Asia region. So yeah, this is the result from the trend analysis for temperature, precipitation, and stream flow for different time scale, dry season, rainy season, and El Niño. So both minimum and maximum temperature, we can see that the significant trend, increasing trend of temperature over the Tonle Sap basin. On the other hand, rainfall and stream flow, even though it showed the increasing trend, but it's not significant, except the stream flow in the dry season, which is increasing significant. Yeah, this is the temporal trend and variability of the basin scale, seasonal, and annual, the maximum and minimum temperature. The above figure is the maximum, and the below one is minimum temperature. So obviously, we can see that the increasing trend of the temperature for both minimum and maximum temperature between 1990 to 2017 for the last 2 decades or 3 decades. And the temporal change of the temperature here is have strong correlation with the ENSO phenomenon happened in the study area. For example, in 2010, when the El Niños happened, so the temperature seemed to be increased. But in next year, 2011, which is La Niños happened, which is a huge flood happened in Thailand, AIT, and also impact to Cambodia. And the temperature you see from here, it seems to be decreased. And this correlation also can be seen in the precipitation. For example, the last figure here. So in the temporal trend and variability of the rainfall for different time scale, MAM, March, April, May, SON, September, October, November, and on annual scale. So the interesting point here, before wet monsoon from March, April, and May, the rainfall is decreasing. But after the wet monsoon, from September to November, the rainfall is increasing. And it's also contribute to the increasing in annual rainfall. So this might be impacts to the agriculture activity inside or around the Tonle Sap basin. And if we look at the right figure, which is the comparison of long-term mean monthly rainfall between 2001-2009 and 2010-2017. So we compare those last 2 decades, and we found out that from February to May, the rainfall is decreasing. But from September, from October to January, the rainfall is increasing. So and this is the special distribution of long-term mean rainfall. So the last one is for 2001-2009, and the right-hand side is from 2010 to 2017. So we can see that in the early monsoon rainfall, so the rainfall have been decreasing around 80 millimeter across the river basin. But after the monsoon rainfall finished, the rainfall is start to increasing across the river basin. So the change of precipitation and temperature, it also impacts through the change of hydrological pattern in the river basin. So you can see from here that the flow in the May, June, and July start to decreasing. But the flow simulation on the September, October, and November it's increasing because of the influence from the temporal change of precipitation, and of course the annual also change. And this is the comparison between the long-term monthly mean monthly stream flow between 2001 and 2009 and 2010 and 2017. Again, the stream flow from April to August, it's so decreasing, but from the October to December, it start decreasing, increasing, and also the flow, peak flow timing also delayed for 1 month from September to October, and the peak flow also increasing. That might be impact to the fishery production in the lake. So come to the conclusion. So we can see that the temperature across the river basin have been increasing around 0.15 degrees Celsius per decade since 1990s. And we also have seen that the temporal change of precipitation and temperature, it's also impact to the flow pattern in the river basin. And the interesting is before monsoon, early monsoon, rainfall is start to decreasing. That might impact to the agriculture activity and agriculture production and national economic development. And after the monsoon finished, rainfall also start increasing. That might be prolong the flood season and also impact to the harvesting season in the agriculture activity inside around the Tonle Sap Lake basin. And the flow volume, also we can see that it's experienced the upward trend. Yes, that's the end of my presentation.
Thank you so much. Thank you, Raxme. Do we have any questions to him? We can take one quick questions. Yes, sir.
So did you do some bias correction before inserting the satellite-based data in the SWOT model?
Actually, thank you for your question. We did the validation of that satellite-based data in another study, but we do not do any bias correction. We just do it, how to say, directly compare to the available data from the ground-based station. For example, we have 5 stations in the river basin, and we do the interpolation of the rainfall data to the point of observation, and we compare it based on the several time scale and also based on the special time scale, and to see how the correlation between the observed data and the satellite data can correlate and can be used for further analysis. Yeah.
Thank you so much. Let's give a big hand to him. Now we have the second last presentation, I believe, from Firas. He will be talking about precipitation disaggregations and its evaluation in terms of performance of this stormwater management model. He is from Technische Universität Dresden. Sorry, I mispronounced it. Germany.
University of Dresden.
Maybe Technical University, right?
Yes, Technical
Okay,
University of Dresden. Thank you very much. I think the sugar in the blood is getting low, so I will ask maybe 2 brainstorm questions before starting my presentation. One is, do you have faced in your research any problem with data availability? And the second question is, do you think that high quality data is really needed sometimes for your modeling to produce results, or is the low quality data sometimes also works? So the idea is, as you see climate change is happening, we have already the climate change affected the rain patterns, and the seasons have been changed a little bit, and extreme event became stronger, comes in a different time, and this weather, dry, wet, is also changing. At the same time, we have a problem with increasing the urbanization. So cities are now accommodating more people than before, and this is actually making an impact on the our infrastructure and everything. So transportation, sewage system, water, cities, and if there is a difference in the precipitation patterns or the patterns and or the increase in the amount of precipitation, our urban drainage system are not able to take all this amount of water, beside other factors. Now, one of the ideas here is to focus on working with data. I mean, the model at the end is one of the models could be used, but the idea is how to work with data that and to produce a high quality result that might be also working in places where you don't have a good quality data. Most of the time for urban modeling or for flood modeling, you need hourly data, 10 minutes data in order to understand the behavior of the model. Most of the cases in many countries you have, as a lecturer, you have daily data. But this daily data, this one number per day, is not enough to understand the behavior of the flood events. So what we do in places where we don't have data, what we did is to work with a part of the city of Dresden to work on urban drainage area there. And why we have selected this area? Because this area has a high quality precipitation data. You have 1 minute, you have 10 minutes, you have hourly data, and you have daily data. And the reason behind this is we wanted to use a weather generator, I'm going to speak about it later, to produce data, and we wanted just to compare the result. Is the weather generator also working and giving similar results to the existing high quality hourly data or 10 minutes data, or this is a big difference? Yes, we did already some evaluation for the data quality. We compared the stations because there are few stations have been selected for the work. Climate stations, mainly precipitation and temperature. Temperature is always okay because you can get it from different models. The problem is with the precipitation data. And we wanted to compare first the precipitation data in these stations to see if they are more or less similar. And also we wanted to generate synthetic data similar to the precipitation data and try to compare them. What's the synthetic data and why we are using weather generators? We need a weather generator to generate data for us that has a similar statistics to our observed data. And why we need this? Let's say we go to a place, we wanted to make flood modeling, and we have in this place only 10 years of available data, and these 10 years full of gaps. And in this case, we take what they call weather generator to generate synthetic data, has a similar statistics to the observed data. But we need to check if the quality of this data is also matching our observed data. So we need also some kind of high quality short period of data. Talking about we use data word a lot here. So first you have a low amount of data, you put it in the weather generator, you generate synthetic data for the base period of time, and you can also use the weather generator to generate future scenarios. This was the first step. The second step is to use a disaggregation tool. What's a disaggregation tool? The disaggregation tool is the tool or a model can make this one number that we have per day to make it 24 numbers as hourly data. So first we go to a place, we generate synthetic data, and then we work with our daily data and make them, work with daily data and we make them hourly data, using some specification from the observed hourly data. And we need this because our urban drainage modeling or our flood modeling needs hourly data, so we need hourly data. And we have to use a disaggregation tool. This one is Hitus Minutes, one of the tools we can, it's an R package, but there are also some other tools can be used. And then we use this result to put it in the stormwater management model. So in the stormwater management model, we use different set of data. One is from the already observed data. Another one is from the future generated data, because the weather generator generated for us also different set of data for the future, for the midterm changes and long-term changes. Yeah, I will go back to this slide here to just explain the structure of the work. So if you see here, this is normally our daily data available. And and we have already hourly data. A little bit of hourly data we generate, we have made a disaggregated data and compare it with the actual available data from the station, and then we use it in the stormwater management model. And then we use Lars weather generator to generate future change scenarios, and we use all this result in the stormwater management model to see if we have already floods, what's going to be the future? Are we expecting more floods, less floods with the data set that we are got from the weather generator or not? Yeah, here this is the recipient 2.6, 2.4, 4.5, 6, and 8.5 is about the emissions. This is the IPCC report. The IPCC considered this a classification after 2014. Before that, they were using scenario A or B or AB. And here we have used the 4.5 and 8.5 for 2 periods. The first period is from the around 40s to the 60s, and the other period is at the end of the century. Yeah, and the result here we have made already generated the baseline data. The results are sometimes very good, sometimes not very good, depends also on the month, and but most of the time the months where we have precipitation data, high quality or extreme events, the model was behaving okay. And if we go to the comparing the result of the observed and the baseline data at the 2 minutes left, then you see that the quality of the result of the weather generator is still good. This is also for the, this was for the wet, and this one for the dry spell length. And also the weather generator gave very good results. Now, when we come to the disaggregation data, the model of HITOS minutes were giving different types of results. Some of them were very good comparing to the data that we have. Some other part of the data was not really that good. But in general, because this is one of the problems when we work with different set of inputs. Yeah, and then we only compare the extreme events. We found that the extreme event that from the observed model were a bit higher than the synthetic data. And also, if we go to the extreme event of the flood, we see the disaggregated data and the observed data. We see that the observed data, the model always gave the high peak before the existing event. So it was like few hours in advance in the model. Yeah, and then July was one of the months that the results were a bit interesting, where we have major big events and flooding in this month. And this is also the future scenarios where you see also some of the cases was a differences between two global climate models with the extreme events. Yeah, as a conclusion, the Lars weather generator downscaling was very good for disaggregating for downscaling the data, and also the HITOS minutes also was very good for the disaggregating the results, and the performance were okay. Sometimes the results were good, sometimes were not good, depends on the months, but for the extreme events it was very good in catching the value. This is the references, and thank you very much for your...
Quick question, and other question we can entertain during the panel discussion. Any quick questions? Yes?
Too many questions. Okay, so I have question is that how you choose the GCMs for your data generation, because did you do some sensitivity analysis for your region? And what do you think that how uncertainties, especially for the longer term, could be addressed in this disaggregation process?
Thank you very much. Both very interesting question. The First one is how to select the GCM. Actually, this is a big question. Depends on which model you wanted to use at the end, because GCMs are designed differently for each purpose. Some of them for agriculture, some of them for economy. So you need to know in which direction you go, and then you decide which GCM to select. The second question about the uncertainty, actually, there is a high uncertainty. You are working with future data based on a model, so the data in the future is a kind of a scenario that you are not sure about, and then you disaggregate this result using also a different kind of data set of scenarios, so the uncertainty is high. But it's important to produce data and some research for places where you don't have enough. So if you go to places where you have a lot of data, there is a lot of research, but if you go to other areas where it's limited to data availability, at least you are doing something for the region. Thank you.
Thank you so much. Let's give a big hand to the speaker. We'll go to the last speaker of the session, Solomon. He will be talking about water accounting plus and its case of 8 river basin in the Philippines. He is from UNIHC, the Netherlands. Yes, please go ahead.
Hi, everyone. My name is Solomon Soyum. I'm from IHE Delft in the Netherlands. My talk today will be about the application of a water accounting tool, what we call Water Accounting Plus, for developing water accounts for 8 river basins in the Mindanao island of the Philippines. I will introduce what Water Accounting Plus is first, and then I will go through the material methods and followed by result and conclusions. So water accounting is defined as the systemic acquisition, analysis, and communication of data and information relating to the stocks and fluxes of water. Thank you. Okay. So water accounting, in short, is about data collection, data analysis, and communication of its results for making information available to stakeholders. And water accounting plays an important role in the integrated water resource management cycle, first by answering a question in the water resources issues assessment stage. What is the current state of the basin, the river basin, in terms of available water, including its spatial and temporal variability, water consumption patterns, and what are the key indicators of the water resource situation of the river basin. And second, on the water resource policy development stage, by answering the question, how will planned development affect the water resources? And finally, on the monitoring and evaluation stage, it answers a question like if improved practices implemented in the river basin have the required results. There are many water accounting frameworks developed in the past, and these frameworks can be grouped into two based on how they define water resources and how they measure water consumption. The first group is called flow accounting, where the accounting is only from blue water sources. So water stored in the reservoirs, water flowing in the rivers, in the lakes, and aquifers. And the second accounting method is called the depletion accounting, where this is a kind of water accounting framework which tries to track water depletion or consumptive use of water as opposed to abstraction. And this means like it also concerns water from the green water sources, not only blue water sources. Sorry. So as I said, there are several water accounting frameworks developed, and some of them are based on only flow accounting, some based on depletion accounting, and some combine the flow accounting with depletion accounting. And the application scale is different from river basin to regional and national level. So when I come to Water Accounting Plus, it's a water accounting framework developed by IHE in partnership with the International Water Management Institute and the United Nations Food and Agriculture Organization. Its geographic domain is river basin, and it's based on a combination of both the flow and the depletion accounting. And in this figure, you can see the whole methodology of accounting, Water Accounting Plus. The data acquisition is mainly relies on data from remote sensing products of the components of the hydrologic cycle and other open access spatial data which feed into a hydrological model, what we call the soil moisture water balance model, and the results are presented in the form of standard sheets, graphs, tables, and maps. So we apply this water accounting tool to develop water accounts for 8 river basins in the Mindanao island of the Philippines. And the water resources of this island is characterized by considerable variability in terms of temporal and spatial water availability. So we consider several remote sensing products for precipitation, evapotranspiration, and also for the change of storage for this island. And based on how the combination of this precipitation, evapotranspiration, and change of storage close the water balance gap, we selected for precipitation GPM, for evapotranspiration SEPO products, and the mean of the change in storage from 3 GRACE solutions. And land use, land cover is one of the main important inputs to water accounting, because we characterized the water consumption production based on land cover classes. So when I come to the result, first we see that the precipitation, evapotranspiration, and the water yield, that's the difference between precipitation and evapotranspiration for the 8 river basins. As you can see, all during the monthly or yearly period, precipitation is higher than evapotranspiration. And we look at the evapotranspiration. One of the important aspects of Water Accounting Plus is also to split evapotranspiration into its blue and green components. So green evapotranspiration is part of the evapotranspiration which is satisfied through precipitation, so direct precipitation and precipitation stored in the soil moisture, whereas blue evapotranspiration is part of that evapotranspiration which comes from either artificial supply or abstraction of groundwater by root depths of trees and forests. So when we look at for the one of the big river basins out of this river basins of Mindanao Island, the Mindanao River Basin. So in this figure, you could see for each land cover class which is present in that river basin, and here you could see the blue is the precipitation that land cover class received, the green is the green evapotranspiration, and the blue is the blue component of evapotranspiration. So you can see that all the land cover classes in this river basin produce actually a runoff. So that means the evapotranspiration is less than the precipitation. And one of the main outputs of Water Accounting Plus is presented in a form of resource-based sheet where we summarize the, I'm sorry, I went to a different. This is not my presentation. Yeah. Okay. Thank you. Thank you very much. So this sheet provides a summary of the gross inflow to the river basin and the consumption and outflow, and also the distribution of the blue component of the evapotranspiration and the green component of the evapotranspiration, and also shows the amount of water available for exploitation, the water consumed by different land, water accounting land use classes. Okay, I will go. And when we look at the key indicators for all 8 river basins, the first key indicator is about ET fraction. That shows like how much water is consumed by evapotranspiration. So we can see that the maximum consumption by evapotranspiration is from the Buyan-Mulango River Basin, which is about 74%. The stationarity index shows like if water is being added to the storage or the storage is being depleted. So negative values indicate that the storage is being depleted, but very small amount, 0.2% only. And the basin closure indicates that how much water is being consumed within the river basin or stored in the river basin. So 100% means like all the water flowing into the river basin is being consumed or stored. But if it's less than, then the remaining part is going outflow of the river basin. And available water indicates how much water is available to be exploited. The managed water is what is the percentage of the water being managed at the moment, and the fraction is managed water divided by available water. So in conclusion, we can say that the average consumption by evapotranspiration varies from 40 to 74% in the 8 river basins, and all the river basins have positive yearly average water yield, with the minimum around 400 millimeter per year and the maximum close to 1,500 millimeter per year. And the availability of water shows both temporal and spatial variability. The monthly variability is more pronounced than the annual variability. And the basin in the northern part of the island show more variability, more water availability than the basin located in the central and southern part of the island. And research shows that this island is highly vulnerable to impacts of climate change, and the water accounting assessment suggests that there is a need for strategies focusing on water productivity and storage capacity to mitigate the impacts of climate change. Thank you very much.
Thank you so much. Let's give a big hand to him. We can now have a discussion together. Please take your seat. Now we'll have around 10 minutes on for panel discussion. We are on time. That's a big thing for us. So it's now the floor is open for any kind of question related to their presentation or related to the theme or for any opinions for now. Yes, please. I can see the hand raised. You can be specific to a speaker or in general.
Yeah, okay. This question is for Solomon. Hi, I'm Wendell. I'm from the Philippines. I'm from Mindanao. I was just curious if your results were ever corroborated with observed data from any government agencies in the area.
Yeah. Okay. Thank you very much for your question. Yeah, I didn't present it here for the sake of time, but when we selected the remote sensing products, what we did first was compare precipitation with observed data, which we got from the island. Also precipitation, we got some data, not exactly coinciding period, but for a different period, so we compared that. And also we looked at how the water balance is closing using these 3 different remote sensing products. Yeah, especially the precipitation data agrees very well. The evapotranspiration data, as I said, the period was different and the values were a bit high from SEBOP, but considering the water balance, how they close the water balance, we selected CEBOP with the best data compared to the others.
Any other questions? Yes, I can see a hand raised here.
I have a question to my colleague, Dr. Solomon. So you have shown the definition of the water accounting, not only for the natural system part as well as for the heavily engineered environment. So this water accounting, how did you include the human intervention part like the dam or other water regulation activities for accounting the water balance?
You are the man of the maths, you know.
I'm the last one, so. Thank you very much. It's a good question. We include, human intervention through different means, like, for example, reservoirs modify the amount of water stored in the basin, but also we look at consumption, for example, through irrigation, how much water is consumed by irrigation. When we talk about the blue component of evapotranspiration, we are talking about how much water is supplied to irrigation or how much water artificially abstracted from groundwater to satisfy the consumption due to different land cover classes.
Thank you. Any other questions? Can I ask a follow-up to this? Yes, please.
Well, very interesting, and especially when we look at this blue and the blue plus green water accounting, and I understand water accounting plus focuses on both. Coming back to the blue water account, I mean, I think one of the major issue that we face while doing the blue water accounting, because many a times we are just interested to know it, is that we are unable to get hold of the return flows, because it works as that you have abstraction, you have supplying, and what are the return flows. And this is where we end up doing, various assumptions and estimates on the consumptive part of it. And I think unless and until we really find out the ways, we have the monitoring system in place where we can actually measure such return flows. I think what we end up doing is either we inflate the water account, or what will happen is that the blue water account, sometimes you also end up coming out with the estimate which does not reflect the situation in the basin. So this is just a challenge which I am trying to highlight. You may or may not want to answer this.
Maybe you may not want to answer.
I can skip it. No, thank you very much for that issue. I understand, and this is one of also our struggle, that it's, unless otherwise we have measurements, it's very difficult to verify the results. But what we try to do is, when we talk about blue water, is we look at the transpiration instead of evapotranspiration. So by assuming that the return flow will be accounted in the transpiration, and transpiration is only what is consumed through vegetation. That's why we talk a bit, our confidence is a bit more if you use transpiration instead of evapotranspiration. But I agree that without real validation, it's very difficult to talk about it.
Any final questions? Because I got the information that it's 12:20 and we need to wrap up, though it was supposed to be 12:32. Any last question from anyone? If not, then I have a final question to all the panelists. I give you right before the examination, right? What is the linkage or contribution of your study for climate change adaptation and resilience building at the broader theme of our conference? In less than a minute, please. I will start from here.
Be very specific, please. I think we have to go for hydropower as a source of energy in the future, wherever the opportunity exists. But we have to plan them wisely to reduce the negative effects of these reservoirs, and also we have to manage them in adaptive way in the face of climate change. Yeah.
So this kind of study will help in that way, right? Exactly. Solomon, yes?
this water accounting plus tool is a kind of evaluation tool. So by evaluating different mitigation and adaptation strategy, and by running different scenarios to see if mitigation strategies are really bringing the required effect in the water resource of a river basin, it can be very helpful. So in that way,
Thank you. Rachel?
Okay. So for me, I would say that I would think that one way forward would be multi-sector dynamics, because when we are looking at things at a decoupled state versus when they are being streamlined together, we can see that there are a lot of interdependencies between different systems. Therefore, if we look at everything together, like multi-sector dynamics, it could help us to understand things better, to plan things better, and to operate things better. Okay, thank you.
Thank you, Firas.
I think if we wanted to understand and cover all the aspects of water security, we need more data. Without data, we cannot really achieve our adaptation plans because we don't know what we have. So we need a better quality of data, and we need to work on the areas where the data availability is really low there. Thank you.
Ravi Kumar?
The science of compound extremes on Indian summer monsoon is still in infancy state, and to advance the studies, we need to apply advanced methodology to understand how they are linked and connected, and it helps in understanding how we can better change to that situation and adapt accordingly.
Thank you. Raksme?
Thank you. So I would pick up something from my specific study. So we found, in my study, we found that recently the climate change really has happened, and this is true. We can prove that. And from that, this is the scientific information that can be used for the decision making. For example, for the cropping pattern changes in the river basin, which is the agriculture production, is the important one in that thing. So my study could be contribute to that point. Yes.
Thank you so much. Thank you once again. Just to summarize technically, our session covered the optimal operation for reservoirs, hydroclimatic variability and extremes, co-simulating water and energy system, storm water management modeling, and water accounting. Geographically, it covered from Eastern Nile basins to Ganges Basin in South Asia, Tonle Sap Lake and Cambodian grid system in Cambodia, and 8 river basin in the Philippines. So we had a very enriching experience and the learning from this session, I believe. I really thank all the speakers specifically for being very precise on time, except one case of 1 minute delay. All other were exactly in 10 minutes. Let's give a big hand to them. Also, thank you so much to all the participants for making our session lively, interactive, and I hope you all enjoyed it. And finally, great acknowledgement to all the technical support team, volunteers, and for helping us in various ways. And of course, many thanks to my colleague for being generous and taking all the notes. He will summarize everything in one sentence later on. Thank you so much. Enjoy your lunch, and we'll have 2 keynote after the lunch. Bye-bye.
Hello. Lunch is just beside this hall. Please enjoy. And the keynote session will be held in the Nakhon Rangsit Hall, the bigger one where the opening was held. Thank you. See you.